Hey everyone. So a few videos ago I think I mentioned the idea of working on a really fast sorting algorithm and playing around with some optimizations, that kind of thing, and I finally have some time. So today is the day we're going to have a go at doing it. So the first thing we do when we're going to do some programming is our homework. So I learned about sorting quite a while ago. I wanted to check that there haven't been any sort of fundamental changes, make sure we're using the right kind of techniques. Let's get on to what I've done for my homework. I have a little presentation to show you. So let's give that a shot. Should look something like this. World of sorting. So I kind of have putting all the sorting algorithms into just three kinds. I'm only showing two of them here, top down, bottom up. The other one I would call like left to right. But those three are basically all doing the same thing. And the differences between them are just those little implementation details. They're not really doing different sorts. So I'm going to have a look at all the algorithms that exist out there and put them into these different buckets. Look for a spot where we could do something slightly different, or maybe choose one that's interesting and try and optimize from there. Two kinds of sorting. We got the comparison sorts, two kinds, top down, bottom up. But within that, you can also do it by comparison, meaning you got two objects that is this greater than that using a less than function. Or if we know we're working with numbers, it's a value, you can start doing some trickier things based on the fact that what you're comparing is a numeric value. But let's start at the top of the comparison one, in the top-down area. So Quicksort, well known. What it does is it picks one item from all of the list of your unsorted items, pulls it out, puts the larger ones to one side, smaller ones to the other. So it's divided in two. Divide and conquer, repeat on each of those. Partition, solve. Simple. Quicksort. Bottom up, canonical one is going to be the merge sort. So this is where you continually split it, and usually in half, all the way down. It's just a method of dividing it up into small pieces until you get to your base case, your smallest one, which could be just like a pair of numbers. You put them in order, and then what you do is you take the previous solutions, the two smaller solutions, and you merge them together. So you're starting from the bottom, merging back up. Cool. So the difference is that like Quicksort can be done in place. What you're doing is you're walking from either end, normally swapping items when one is too large or too small. So you're putting two items in the right place at the same time. You could write to external memory as well. Like you go through, find the ones out of place, write them to a separate array. So what's nice there is that you're going to do reading from one part of memory and writing to another. So your reads are cache friendly, but it's a bit of faff. So that's what my technical term you'll see through the slide is faff, meaning you've got to have a bit of extra code and you've just got to do more admin. It becomes a bit messy. For merge sort, you almost always need the external piece of memory to write to. That's when you've got your two sub-problems, you're going to merge them or write in a separate piece of memory. You can do it without the separate one, but it's quite tough. You've got the two things that you want to merge that are already in the right bit of memory, and you have to do little cycles and things, and it's just a bit ugly. In place, loads of faff. There's one that I didn't know of beforehand, but the natural extension of Quicksort, I didn't know the name of it. It's just sort of what you do, where instead of picking one pivot and partitioning it to the left and right of it, you pick multiple pivots. And so let's say you picked like 3 pivots, then you could split your array into 4 different sections. And so each of those could be ordered, right? So there's the smallest, a bucket with the second smallest, third, and so on. And that's called sample sort, which was news to me. So fine. It's what you'd do if you felt like trying to pass through the array fewer numbers of times and do more work each time you pass through it. And so bottom up, doing that, I don't know of this. So that would mean that you're doing a merge on multiple, rather than just 2 arrays being merged together. You could do it across, say, 4 at a time. Yeah, I don't know what it'd be like. I don't think anyone's tried it. I haven't seen it being tried. I guess I'm calling it merges sort. Yeah. So something else I put in here is actually the depth of things go. So you're always passing across the array once for each of these. You split it in 2 with Quicksort. You still have to sort the left side and right side, so it is a pass through every single item. You pass through it once. And then the only thing that changes is how many times you have to do that. So that's the depth of the search. Quicksort should be log n if you're roughly splitting it in half. But let's say the pivot you chose, that one item you chose, was always the rightmost or near the right-hand side. Most implementations do like these medians and medians to pick it. So it's probably going to be in the last, the worst case would be like the 9th last maybe. And you've split it in two, but you basically have to resort almost the whole thing again as you keep going down, in which case your depth would be size n, and that's the worst case for quicksort. Merge sort doesn't have that problem because you are dividing in half strictly. It's not based on a value that could get unlucky with. Quicksort implementations, PDQ sort is the big one. That was the one that was the Golang standard. It's just a normal quicksort with checking for some patterns. So it checks for things like, is it reversed, is it already in order, all these simple cases, like one thing out of place, that kind of stuff. And then it also has a few other heuristics, like if it's looking bad, like you're heading towards that worst case of an n, it can flick to a heap sort, which I'm not going to list here. Heap sort is an example of like the left to right. That's got all your insertion sort, bubble sort, all those sorts of things which can operate the little sorted portion to the left-hand side of your array that it slowly increases inside. Heap sort's one of those, but it's the login version of the left to right sort. Cool. PDQ sort. Anyway, it's out there. It's fine. It's just a quick sort. All right. Next up, your basic best merge sort that's around seems to be Tim sort, named after Tim. Ooh, yeah, right. My bugbear is people naming sorts after themselves. You may have already realized. So Tim sort is a merge sort, and the reason it's a bit quick is that it treats parts that are already sorted, that are a run of ascending values, that don't need merging. It kind of can skip over them. That does not seem like an innovation. Like, it is just the most basic thing. So in fact, I brought with me my book of The Art of Computer Programming, Sorting and Searching, second edition, because I'm pretty sure exactly what that Tim sort is talking about is like your most standard technique. So Knuth in his book usually talks about sorting of lists or linked lists rather than arrays, and there, like, it is the most obvious speed up or optimization for a linked list, in that if you've got one that's already sorted, another sorted, we're going to merge them, all you have to do is make one link between the two and you've got your new array. Like, or you take an ascending slice that's going to go inside another one, you only have to trim the either ends, remove the links, put them in the other, right? It's like clear as done. So indulge me, I went to check external sorting, optimal sorting, internal sorting. Sorting by merging, page 158. So I will just say, yes, it is in there. And there are some other optimizations, and I just read through it again. I can't remember what they were, but they're exactly what was being done. I remember the other optimization. Yeah, and so the other method, which Tim Sort says is like somehow interesting, is that it actually strictly works bottom up. So it takes it in pairs of numbers, and then you merge two of them to get something of size 4. And rather than having done it recursively, so you end up doing those divisions done sort of created via recursion, and then as you backtrack, they get all the merging done. Instead, you actually start from the bottom and you create your own little stack. So it kind of is almost working left to right through the array. It's just what you do bottom up, and that's precisely the way Knuth described his sorting algorithm. He does not do recursive algorithms. He uses a stack and builds them from the bottom up. So Tim Sort, you're just like pick and mix a bit of Knuth. Okay. Quad sort, for a second I thought it was going to be a bit like a merges sort, doing 4 at a time. It's not. It is an optimization for the base case, effectively. It's just be able to merge 4 numbers really fast. Then we move on to what you can do if you know that you're sorting numbers rather than values. Rather than arbitrary values. And radix sort is the first one. So a radix sort could be done least significant digit up or most significant digit down. The one I was taught was least significant digit, and that's quite fun, where you sort by like basically your lowest decimal, your lowest radix. And then having done that, as long as your sort is stable, you can then sort by the next one and so on. But hey, getting ahead of myself, because this is most significant first, which means it's the highest digit value that you sort by. And that means that you make a value that you're going to split your array by, and then you put it into buckets. So you will say, let's say your radix has got, say, 4 values in this picture. You'll put the smallest ones to the left of the smallest of those values of the radix, and second bucket, third bucket, fourth bucket, which is exactly what sample sort is doing. So the difference between radix sort and sample sort is that sample sort is going to pick pivots, values that exist in the array. Radix sort is just going to create those values based on the fact that it's using however many bits. So yeah, radix sort is in place. It has a bit of faff because you have to deal with the buckets that you're putting it in. Value-based merge sort, I couldn't think of how you would do that differently from a regular merge sort, other than you can use like bitwise ops, which is kind of probably what quad sort did. Implementations of radix sort, however, there are loads. So there is a scar sort, there is vx sort and vq sort. The v's are for vectorized, so all of those are just trying to use simmed operations. That's like your AVX or your SSE instructions. So today I don't think I'm going to have time. It's just my lunch break. This is what I'm doing. I don't have time to go through and do the simmed ones. So what I'll probably end up doing is making a sort that's at least quicker than PDQ sort, quad sort, tim sort. These sorts of non-simmed ones, and then we'll do maybe a second video where I can add the simmed instructions. And so somewhere in between is this radix sort, least significant first. And I was saying it's kind of. It's not necessarily top down, because you're doing these passes across it and putting it in buckets. You'll do the same thing here, but the buckets are no longer ordered by value. They're only ordered by the last decimal, or not the last decimal place, the last radix place, I should say. And so least significant first is slightly different. If you're doing it to external, it is really easy. If you're doing it in place, then I think it is quite tricky. Because of the stable sort. I'm starting to doubt that now, actually, because it may be that you could do it like quicksort, because this is just, that's all radix sort is. It's just quicksort with a different way of making a pivot. So I should say, anyone who says that like there's something, this is a log n, this is a big O n algorithm, this is n log n, it's like that's bollocks, because this is operating on 64-bit numbers or 32-bit numbers. Sure, the depth is k to do with the number of radices, if you like, but that's just going to be like log n, because you need 64 bits to address it, so there's a limit on the array size as well, and it's like, it's the same thing. So anyway, for the least significant first, I think what you could be doing is, like quicksort, doing swaps. Now, normally with quicksort, it's not stable because you're going from the far right and the far left and working inwards. And so when you swap, if you had two things in order over here and both got swapped, they would be in the other order in the resulting array. So that's the lack of stability. But if you found that bucket start or from the pivot position and you're working left to right through both your arrays doing the swaps, I suspect it should be, as far as I can tell, it will be stable. So to do that with quicksort, you would have to first go through, find your pivot, and then go through another pass, do the count of how many are larger than it, and then you would know where it began, and so you could do a stable quicksort that way. And I think you could do the same with radix if you'd need to find the bucket positions in the existing array. Not going to try and do it though, still a bit of faff. What I'm going to do, I'm going to start in this blank area, or it was a blank area over here, where radix sort, let's go through, I've got more slides that show the depth, but basically we'll do a quick sort that exploits the value, the fact that we're using integers, so it will cook up values rather than selecting a pivot. And we'll try and make its depth the minimum of the two, k or log n. So we'll try and get the best of both worlds. That'll be like our pattern business. All right. I'm just going to run through now how I intend to approach this sort. So this is how we're going to tackle it. This is step 2 of coding, right? We've done our homework. Now we do our brainstorming. Example array, unsorted. So this now, because we're doing value-based, this is kind of what we want to do, where we represent it as the bits and see what kind of tricks we can come up with to improve things. So just mute my work computer. In a radix sort, let's say it's a radix of a radix 4, which is based on 2 bits. Radix 4 meaning it has 4 unique values. So your first digit of 2 bits is going to be looking at these two, and we can sort based on that, right? And when you do this, you put all the ones that were 0 zeros into bucket 1, the 0 ones into bucket 2, the 1 zeros in bucket 3, and the 1 ones in bucket 4, which didn't exist in this. And now you've got your smaller stuff on the left-hand side and your larger stuff on the right, or in each of their own buckets. And then you would move on to the next digit, right? Digit 2, we're going to do the same thing. You see only 2 of the 4 buckets in use. So there are some irrelevant bits. We noticed that we didn't really make use of this. There were 2 buckets that were empty. Same with this second pass, same here, and it would be the same down here where they're all 1s. We wouldn't be using the buckets either. First optimization seems to me to be that we can go through and choose the radix, but rather than having a fixed radix, we can adapt it to the data that's in the array. If we're willing to do a pass through the whole thing, we should be able to determine that some of these bits are non-informative. So we can ignore those. And then what we could do is something like this. Cook up digit 1, still using 2 bits, but only the ones that are informative. So we can sort it this way instead. So now we know that we're going to get some 1 1s, some 0 zeros, some 0 1s. So every bucket's in use. We'll be dividing it up, slightly more. So we should be sorting quicker that way. And then we can adapt to whatever is remaining. And so sometimes that will be a digit like on these 2, and maybe in another bucket it would be 2 other ones. But again, we should be able to hit the base cases much quicker. That's my plan. I think that's it, right? We're going to do like this adaptive pivot selection. All right, that's most of the work done, so let's just program it. I've already put in PDQ sort and tim sort. Let's have a peek at those. For the benchmarking, I just have a handful of different cases. There's random numbers, 11 sawtooth segments, so it's just sort of 11 segments disjoint. We've got one with a bunch of repeated values, so only 20 unique values, which means you'll end up partway through sorting, finding these long kind of plateaus in your input. A reversed array, which PDQ sort should be good at, finding the pattern, and one outlet, mostly sorted with just a couple out of place. In terms of benchmarking, so I've got the PDQ sort, which is the standard one from Golang. I have a tim sort implementation in Golang as well. I do have some other ones with SIMD, so based on NumPy, there's a quick sort and a radix sort there that have SIMD implementations. I'm not going to show those yet because first step is just to do better than the existing basic sorts. Tim sort, slower. PDQ sort, faster is your basic one with random. So this is just plotting linear on each. So what we're seeing mostly is the last 2 array sizes. The sizes we're doing are from 100,000, 10,000, 100, million, 10 million. So we're mostly just seeing the million and 10 million examples there. So another way of plotting it down below is doing it as a log-log graph. So there's your input value sizes, and then we'll do a logarithm of the size in of the time in nanoseconds. So what happens there is if we see these 2 straight lines like this, if there's a fixed gap between them, that means one is a fixed multiple faster than the other. There is a third way that people plot them. This is again the same chart as above. The speed to sort per element you're looking for is a flat line would mean that you are linear in the size of the array. So let's have a look. Let's have a look how it's doing. In random, as I was saying, tim sort worse. They get closer together for the larger array sizes. You can kind of see it there. Neither of them is linear. They're both increasing. So they're n log n. Deterministic ascending segments. This means the sawtooth shape. Tim sort actually does better when it gets larger. So there are 11 segments, which means these become very long segments in the large array, and I guess tim sort has been quite good at merging those back together. It overtakes the PDQ sort. It's quite interesting. In fact, its time per data length goes down, and that again will be because it's being more and more efficient as those sawtooth segments become longer and longer. And this is for 20 unique values, and it's almost flat. So it'll probably rapidly put them into like collections of all the same number, and it will recognize that it doesn't need further sorting. So it'll really quickly hit the base case and then stop. Next one is in reverse. Again, PDQ sort actually checks for reverse ordering. So this is one where find a pattern, quickly solve it, 2 nanoseconds per element. Finally, the near sorted ones, same again, like tim sort, and this one it's 5 nanoseconds. So it's doing, this probably isn't finding the pattern. I'm guessing what's happening is, and with a quick sort, it will already have a large chunk that's sorted. It will divide it up, and basically the recursion will end up only having to work on one of the subarrays. So instead of it having to pair up, it's just going to be working on one of them, and so therefore it becomes linear because if you take the sum of each of those divided by 2, then it will be equal to like less than twice the length of the input. So now it is time to code it. What do we want to do? All right, we want a agent. So we're going to have a new file. We'll just call it mySort because I can't think of anything. Quick sort for a slice of unassigned ints. Ints. Just ints. So we want a function that's going to pass through the array once. Okay. So it passes through the input slice. And what we want to do is we want to find out what the best radix is. So to do that, we need to know whether any given bit is all zeros or all ones. So so input slice once and returns a pivot value. It should accumulate the bitwise OR. So the bitwise OR means that if either of them have a 1, it will have a 1. And so we should do that across the every single value. And then the result will only have zeros left when there are zeros in the input, in every single value. Yep, bitwise OR of every value. Bitwise AND of every value. Let me just double check what I'm thinking here. Is the bitwise AND the equivalent for the zeros as it was for the ones before? No, the ones rather than zeros. So you AND it. Every time it hits a 0, that one gets clobbered. Anything that's still a 1 at the end is a 1 in every single value. So things that are 1s in the ANDs or 0s in the ORs should be ignored because they're uninformative bits. Right. Just to start with though, let's just have it return the average of the two numbers. Which I don't think is right. It's not even close to right. The one with bitwise OR is going to be larger than the maximum value. The bitwise ANDs are going to be smaller than the minimum value. And there's no guarantee that the average of the two is even anywhere within the array. But you know what? Let's just get some code out there. Each iteration of quick sort should use this pivot selection function. Okay, what happens after that? Do pivot selection, then we have to split. So the sorting function should then call another function that performs the partitioning around the chosen pivot using swaps. Now, from the outside in, let's just do it. Okay, that should get some code out there. Add a unit test to sort test. Go and check, and run it once. Okay, fine. So that should be enough to get us started. I mean, I must confess, I think I could have typed in the solution faster than it was to type in those words. But, you know, modern programming, enjoy. What else can we do? So we want to be quicker than PDQ sort, which means we're going to have to handle patterns. So during that first pass, and in fact we have to do a lot better because PDQ sort and all these other ones are doing these other quick sorts are doing medians of medians. So they just sample about 9 values, I think 3 values, and they do that 3 times. So they don't have to pass through the entire array. So we should need to get a whole lot of benefit from scanning through the entire array. Just getting this arbitrary pivot is not good enough. So we should be able to tell if it's reversed because we're going to go through the entire array. Yeah. What does it look like? We should therefore also accumulate whether the previous value is greater than the current value. And then if it is every single time, maybe we could count how often that happens. Compare it to the number of values. That might be useful because then it will also tell us if we're nearly sorted. Yeah, we'll do that. So we can accumulate how many are descending, we can accumulate how many are ascending, and that would let us abort early as well if it's pre-sorted. I wonder if... Yeah, so now I'm thinking about that, where I was talking about how a stable sort, we could choose to start like swapping from the left or swapping from the right, where one of them, if you swap from the outside in, from the right, you end up switching all the values, flipping their order around, losing stability. So imagine that it was mostly sorted on the right. You flip all those smaller ones, they're all now unsorted on the left, which feels bad. Whereas if it were descending mostly on the right, when you flip all the small ones, they become correctly ordered on the left, which I think has more chance then of reaching the base case. Is that right? Maybe. Which means that, let's say you checked from your, you don't know where the pivot position is, but if you did, if you knew where the pivot position was and it was more ascending on the right than it was descending, you could choose to move from that pivot forward rather than the pivot back. So that's motivation to scan through it twice. Choose your pivot, find its position, and then also, yeah, is that 3 scans? That's too many. But there may be some serious speed ups now, because then you're basically making the best choice every time. Sort of was this thing, quick sort ints. Yeah, it looks fantastic. Haven't actually read it, but sure. I was saying like full on to recursion. That's going to be so slow. No, you cannot do that. Okay. I is less than I plus start I, or is odd equal to, and is and equal to it, and then yeah, that is what I asked you to do. I don't know if it's sensible, but it's what I asked you to do. Partition from the outside in. It must have it right. This is everywhere in every textbook. Let's run my test. I don't think you did run the test, even though I asked you. Oh, I see. Right, fair enough. Fail. How did you fail this? We need to make some more unit tests then. I didn't think we'd actually need other unit tests. Oh no, my lunch break's nearly over. This is taking a lot longer than I thought. Alright. Instead, let's cook up the actual value I want first. So the value I want is going to be the value which is going to be not the highest order bit that's set in both. It's almost that. It's the highest order bit that is set in or and not in and. Okay, if the pivot is 0, then we're finished, because it means that we've gone through and all the values are the same. Correct. Okay, I wants to go from high to low rather than low to high. Interesting. We're left shifting 1 by I to make a mask. So it starts off small. Yeah, good point. So it's going now to the highest order first, which is what we want. And then it returns that, and that will be smaller than the highest. Yeah, okay. So we're doing a radix 1, radix 2, a single bit. It's probably going to still die, but layer of recursion by iterating not one layer of recursion, one recursive call. Let's be clear what we want. Side of the slice with a recursive call only on the right-hand side. Very well, I shall trust you, which is not necessarily a good idea. Alright, well unfortunately my time here is just about done. Let's make the small unit test to find out why it's broken. We will get test sort test sort 4 values. Yeah, thanks, out of order. So I believe that this is probably right. We need unit tests for the pivot from bitwise average, don't we? Especially with this suspect stuff in here. Add and run a unit test for pivot selection. Maybe I should do it myself then. Pivot should not be 4. If it's less than or equal to 1, or pivot's greater than or equal to 4, yeah, it should be between 1 and 4. Whoa, dude. Pivot test. All right, good on you. Do it this way. I can run you. So let's check what pivot it makes. From 1, 2, and 3, it wants number 2, and it found it. From 8 and 12, it doesn't really matter. It wants 4. No. Oh god, it's returning which bit it is, not a new number with that bit set. Of course. It's doing what I said, not what I want. So it's going to be, or is going to be that, and is going to be that. Where the hell do you get the first bit that differs? Oh. Yeah. We have to keep all the bits that are the same. The logic's not quite right. So we want, yeah, it's not the highest order bit that's set in either of them. That's the one we want to be working on. But we want it to be all ones above that. Is that correct? No, we want it to be equal to the shared values above that, 1s and 0s. Okay, so let's do this. Bit pi should be set to the comment between amongst all values. which is going to be ands and ors, isn't it? Based on, it'll both be the same. Yeah, okay. So the AND value creates a mask, subtracts 1 from it, and then exclusive ORs it to switch it. Okay, yeah, fancy. I wouldn't have done it that way. Base and also set the highest bit. Is that right? And do it, no, OR with it. Yeah, okay, let's try that. I expect it to be 8. It's going to have 1 in the position. They don't differ anywhere. No, they differ in the leftmost one. So it should be a 1. So they're different to 30. They're different to 4. But they share a 1, so then it should be equal to 12. No different bits, pivot is 7. This one is going to be 2 is the highest bit, and then set to the common bit. Well, highest, let's just not make this up. The highest common differing bit is 4, plus shared bits is 12. And this one has no higher shared bits. Okay. Four values now sorts. Quick sort, large random, sorts. Okay, so now it's working. I will have to come back. Now let's do the benchmark. We'll do the benchmark. Matching existing tests. I hope my random numbers are all positive because we're using the sign bit just like any other at the moment. Yeah, I think we're okay. Good. And the benchmarks, and we are nearly finished. So what are we not doing yet? We're not finding the pattern, so we'll be a lot worse on the pattern detection part. In fact, it's not going to be great at all, is it? We're using a radix 1, radix 2, 1 bit, and oh yeah, thanks. And we're not doing anything else, so we're not doing anything particularly smart. But the basis is there, so after this, it's pretty straightforward, I think. We'll go to add the pattern stuff to this read pass, and then we could start the optimizations where we... Ooh, what should we do? First thing will be making sure we do this loop nicely. We could read multiple values at a time. It'd be really easy to do this in Sim, to like vectorize it. So that will be tempting. I should be able to make a smart reverse. I think if we detect that the array is reversed, then we can really rapidly do that. So I will add these, and then I will jump to. So it is, yeah, quite a bit slower than the other two. I'll prove the terminal command. Sure. It's not too surprising. We probably ought to then start jumping in and actually doing the profiling, finding out where it's worst. I mean, there's no base case yet, so it's doing quicksort all the way to the bottom, which is quite crazy. In fact, that's almost certainly it. We should add a fast insertion or something, base case for it. Way off. It's a factor of 10 for the small ones because, again, that's going to hit the base case fast. And for the big ones, it's like a factor of 2, which isn't that bad, actually. I think we could easily bridge that. But unfortunately, it is work for next time. But thank you for putting up with me. We will have to optimize this as a series of videos rather than as